This is a recording for Physical Science Origin of Elements. The universe originated from a single infinitesimally dense point called singularity. This is according to the theory of the Big Bang. But in material perspective, how did everything literally come about? In this session, we will look at the origins of elements. Specifically, by the end of this session, you should be able to demonstrate an understanding of the formation of elements, give evidence for and describe the formation of heavier elements, and demonstrate an understanding of the distribution of the chemical elements and the isotopes in the universe. Similar to how everything evolved from an explosion of space-time, matter in the materialistic world also evolved. The evolution of materials is deeply rooted with nuclear reactions. On the course of the Big Bang, atoms would split into smaller nucleus or combine to a single atom. The process in which atoms fuse into one is called nuclear fusion, while if an atom splits into few smaller atoms, it undergoes the process of nuclear fission. Being one of the fundamental forces in the universe, nuclear force requires high amount of energy to rip apart or combine atoms. This is the very reason why elements evolved as the universe expanded from singularity. During nuclear reactions, emission of energy is always inevitable. Radiation is always emitted during nuclear reactions. The emission of energy during a nuclear reaction is called radioactivity. In representing particles in an equation, we use this formula where X refers to any hypothetical element found in the periodic table. Z is the atomic number. The atomic number can also represent the number of protons. If you may recall, the identity of element changes based on the number of protons an atom carries. And we have A, or the atomic mass. The atomic mass is the sum of the masses of the subatomic particles neutron and proton, since electron has a negligible mass. Radioactivity, or the particle emitted during the process of fusion or fission, dictates the type of nuclear reaction. Radioactive particles may be in the form of subatomic particles, an element, and many others. The following are the most popular type of nuclear reactions. Alpha decay releases an alpha particle. An alpha particle is usually an element released during a nuclear reaction. What separates this helium as an alpha particle, aside from it doesn't have an electron around it, is that it travels in a high-speed motion. Beta decay releases a beta particle. A beta particle is simply a high-speed electron released during a nuclear reaction. And gamma radiation releases a gamma ray. A gamma ray is a high stream of photon, light that is of pure energy, while positron emission refers to the conversion of a proton into a nucleus, releasing a positron during the process. These positrons are much like electrons, but with an opposite charge that is a positive one. Electron capture is a process wherein an electron is drawn towards an atom's nucleus, while bombardment of alpha particle is just the addition of an alpha particle. Identify the nuclear reactions involved in these examples. These nuclear reactions occur alongside the Big Bang. From explosion of singularity 14 billion years ago was also the instant when subatomic particles were created. Subatomic particles in our current understanding form the basic component of an atom, where an atom forms the fundamental part of the material universe. The first element formed when the universe was still young, as subatomic particles began to accumulate as an atom. Hydrogen was formed from a single proton and neutron as the nucleus and an electron around it. Several hydrogen and helium isotopes formed during the early state of the material universe. Isotopes refer to an element with different number of neutrons. Because most of the attributed mass in an atom is carried by a neutron, isotopes are heavier versions of the same element. Example: the isotope of hydrogen formed during the early days of the Big Bang are deuterium and tritium. According to the observation of the cosmos, the universe expanded, redshifting back the idea that the universe expands in an exponential rate to this very moment. Alongside the expansion was also the process when atoms formed and fused. Big Bang nucleosynthesis was the process through which light elements formed through fusion. During the early universe, these fusions of subatomic particles yield isotopes of hydrogen until eventually form the element helium. Nucleosynthesis involved the formation of elements from hydrogen to lithium. Stellar formation happened when the universe started to settle, which formed stars from light elements. Inside the star is where heavier elements from beryllium to iron form. Layers called fusion shells are regions where these elements form. As more elements were produced, new layers add up until the star becomes a red giant. Stellar explosion happens when a star undergoes supernova. Heavier elements than iron requires more energy. Supernova suffices this requirement. As heavy stars already lost their fuel, this is mainly hydrogen and helium, the iron core will start to collapse. As elements get heavier, forming their isotopes through neutron capture, beta decay happens, which forms heavier elements. If the neutron capture occurs before beta decay happens, this process is called S process or slow neutron capture reaction, while R process or rapid neutron capture reaction occurs when beta decay takes place after neutron capture. During stellar explosion, different isotopes and much heavier elements form as neutron capture and beta decay process take place. These elements and fragments of stars during supernova are the precursors for the formation of planets, new stars, and heavenly bodies as a part of the material universe. That's all the time we have for this session. Thanks for watching and see you again in the next one. This is a recording for Physical Science Origin of Elements. The universe originated from a single infinitesimal